Welcome all. So, today we will be looking into the failure mechanisms of the structure elements. Okay. In the last lecture, we looked into the design examples of a concrete and a steel member. So, today we will be looking into the failure mechanism that evolves into the elements during the blast and impact loading. Okay. So, introduction to structural failure. What is structural failure? Okay. Failure we define as the inability of an element or a system to perform the intended function safely. Okay. What we are trying to say is that there is a distinction between failure and collapse. Okay. So, we need to understand the distinction between these two words. Okay. In the design analysis field, failure is defined as the inability of an element to perform an intended function safely. Okay. So, these are the keywords. Okay. Let us say we are designing a column. Okay. So, let us say we have a stout column. Okay. It means that the length is short. Okay. And if we are applying a load, okay, that is acting directly at the center of the section, okay, we are expecting only a compressive behavior. Okay. We are making sure that the compression will occur and there will be no buckling in the section. Okay. So, what will happen into this section? Okay. This section will go into the compressive loading. Okay. So, stresses at all the faces, okay, will be in compression. Okay. So, my requirement, okay, as a designer, I require that this section, okay, this member should be always in the elastic limit. Okay. So, this is my definition of my performance. Okay. The section should always remain in the elastic limit. Okay. So, the performance level is defined, okay, is such that the stresses in the section or strain in the section, okay, always remain below the, or it cannot exceed the elastic limit. Okay. So, this is the definition of the performance of the section, okay, or the functional requirement that it is going to give safely. Okay. It means that once the loading is increased to a level such that the elastic limit is crossed, okay, I will define the section to be failed. Okay. It means that the limit state of elastic behavior has been exceeded. Okay. It does not mean that my whole section has crushed. Okay. So, there is not a collapse of the section. It only means that the limit of the elastic limit, okay, which I have set as the performance of this particular section has been exceeded. Okay. The section has not collapsed. Okay. It can still take increased loading on it. Okay. Only thing what is going to happen is that here the section will be then in the elastoplastic or the plastic regime. Okay. The elastic regime has been exceeded. Okay. So, the functional performance which I have said as an elastic limit has been exceeded. It means that the section can no longer safely hold the load in the elastic limit. Okay. So, this is the called as the failure of the section. It does not mean that the section has crushed. Okay. The entire section has crushed and the collapse has occurred. It can surely take more load. Okay. But when it is taking more load, it might be in the elastoplastic region or it might be in the plastic region depending upon the magnitude of the section. Okay. The elastic limit has been breached. Okay. So, this is the definition of the failure. Okay. And this is the distinction between the failure and the collapse. Okay. It means that whatever performance limit that we have set, okay, whatever limit state function that we have set up for the functioning of this particular system, that has been exceeded. Okay. It does not mean the structure cannot take more load. Okay. Structure can take more load, it can function also. Okay. But the functional performance requirement that we set, that has been breached. Okay. So, this is the distinction between the failure and the collapse. Okay. So, this we need to keep in mind when we are defining the structural failures. Failure does not mean collapse. Okay. It only means that the whatever performance limit, okay, whatever limit state function or performance criteria, whatever we have said, that has been breached. Okay. So, from the civil engineering perspective, okay, failure might be linked to collapse. Okay. It might be linked to cracking, it might be linked to the excessive deformation. It only means that whatever limit state function we are setting, that has been breached. Okay. So, limit state function we can set in terms of deformations, we can set up in terms of onset of cracking, or we can set up my limit state function with respect to the collapse also. Okay. So, we are free to set up the limit state function depending upon the functional requirement of my system. Okay. So, whatever functional requirement we set, okay, when that is being breached, okay, that the structure, okay, can no longer take that much of loading. Okay. The system cannot take that much of loading while maintaining the performance function, then we said that my structure has failed. Okay. It has not collapsed. Okay. The collapse has not happened. Okay. But the intended functional requirement has been breached. Okay. So, the causes for failure, okay, the causes for failure might be the design errors, it might happen due to the material defects, due to the construction flaws, overloading, deterioration of the structure over a period of time, or fatigue loading, or due to the extreme events. Okay. So, different type of failure occur depending upon the what the structure is going to face. Okay. And these are the some of the incipient causes of the failure of a structure. So, categories of failure mechanism. Okay. Instability, okay, the structure might become unstable. Okay. So, normally buckling of slender member occurs, okay, and or the lateral torsional buckling of the beam occur. Okay. If my column is slender, okay, then before crushing, okay, if it is slender, then before crushing the entire system might buckle, or in a beam, okay, in a beam, okay, the lateral torsional buckling might occur. Okay. Remember, we design our beam mostly to resist the flexural capacity, flexural demand as well as the shear demand. Okay. And if there is a torsion across the longitudinal section, normally we do not design for it. Okay. So, if this thing occurs due to any accidental load, mishaps and all, the section is bound to buckle, okay, and there will be a lateral torsional buckling in my section. Okay. Next, failure can occur due to fracture. Okay. Sudden cracking or separation of the structural element occurs. Okay. So, this will cause fracture in the section. Okay. Fatigue. Fatigue is also a major cause of the failure. Okay. Earlier we talked about the ascent curve. Okay. So, in the ascent curve what happens is that as the number of repetitive cycle increases, okay, the structure is undergoing repetitive cycles. Okay. The structure might fail at an stresses lower than the given yield stresses, okay, or the corresponding strength of the structure. Okay. So, due to the repeated loading, okay, there is a fatigue phenomena occurring in the structure and it may fail well below the intended strength level. Okay. Creep. Okay. So, this is a time dependent phenomena. So, there is a time dependent deformation occurring under the sustained stresses. Okay. So, due to this sustained stresses, okay, over a long period of time, there might be excessive deformation in the structure which might lead to the failure in the structure. Okay. Progressive collapse. Okay. So, what happens in the progressive collapse is that the local failure spreads to the system and leads to a system wide collapse. Okay. So, let us say we have a framed system. Okay. So, we know that in a framed system there is lot of redundancy inbuilt in the system. Okay. And we take advantage of this redundancy in the system and we always optimize the section. Okay. So, if we have designed such that my sections are on the brink of an optimized configuration, okay, all sections are loaded such that they are fully optimized, okay, they are taking the maximum loading depending upon the capacity. Okay. So, if one section fails, okay, there will be a redistribution of the loading. Okay. And if the redistribution of the loading occurs and if my total configuration is such that the total capacity is already equal to the total demand on each of the respective sections, so it might lead to a failure in the other regions. Okay. Or it might also happen that some of the sections are having more capacity, okay, but in some of the section the capacity and the demand ratio is almost 1. Okay. So, if one section fails and the redistribution of the loading occurs, then there are chances of failure of that particular section in which the demand to the capacity ratio has already reached 1. Okay. So, if that occurs, then again one more redistribution will occur, okay, and this will lead to a chain reaction, okay, and this will lead to a progressive collapse of the entire system. Okay. So, these are the ways in which a failure mechanism can occur in the structure. Okay. So, compressive failure, so short versus long columns. So, in short columns we will have crushing failure, okay, and in the long columns we will have the buckling failure. Okay. So, if we have column configuration like this, okay, the load carrying capacity is same, okay. Okay. So, the cross sectional area is same, the material is same. So, the load carrying capacity is same, but this long column is susceptible to buckling, okay, and here the crushing will occur. Okay. So, if load is increased, okay, so from P1 to P2 to P3, okay, this section, okay, this configuration might fail in buckling, okay, where the buckling load capacity is given by this equation, okay, this equation we are deriving from the Euler buckling load, okay, and then PCR is significantly less than the P compressive. Okay. So, whatever P we have designed it for, okay, this PCR is significantly less than that, okay, and the column fails in the buckling. Okay. So, this is an example of a failure in the compressive region. Okay. Similarly, there will be buckling in the beams and column. Okay. So, there will be elastic versus inelastic buckling, there will be lateral torsional buckling that we already discussed about, there is the post buckling behavior. Okay. So, here depending upon the slender capacity, okay, the slenderness ratio of the sections, okay, there is a tendency of the reduction in the load carrying capacity. Okay. So, for the compact section, okay, for the non compact section and for the slender section. Okay. So, here if it comes out of a particular value, okay, it will follow the Euler-Bernoulli buckling criteria, and above that the section will behave as a compact section. Okay. So, this is the critical stress equation, okay, for the buckling in beams and columns. Then comes the fracture mechanism. Fracture mechanism we have dealt when we were talking about the composite sections. Okay. So, there will be a crack initiation and propagation. Okay. So, there are different modes of failure. Okay. This way it can happen. Okay. So, this is the mode 1 opening mode. Okay. In plane shear can occur. Okay. So, the shear is acting in the plane, okay, and there will be a sliding along this surface, okay, and this is a case of an out of plane shear occurring. Okay. So, this will depend upon the stress intensity factor, okay, and the failure occurs when the stress intensity factor is greater than the fracture toughness. Okay. And Paris law for crack growth is given out here. Okay. So, this is a reiteration of the failure that we already saw when we were discussing the composites and when we were discussing about the growth of the fractures. Okay. So, opening mode, in plane shear mode and out of plane shear mode. Okay. Then fatigue failure. Okay. So, there are two types of fatigue failure, high cycle fatigue versus low cycle fatigue. Okay. And we have already seen the ascent curve. Ascent curve is nothing but the stress versus the number of repetitive cycle curves. Okay. So, the Goodman relationship is used to determine the failure of the system. Okay. And the Palmgren-Minor rule is used to calculate the cumulative damage occurring in the structure. Okay. So, basically what is happening here? Okay. So, this is the case of a static failure. Okay. So, here the large global deformation and large plastic strain will occur. Okay. There is a low cycle fatigue. Okay. So, in the low cycle fatigue, small local plastic strain will occur. Okay. And in the high cycle fatigue, small localized elastic strain will occur. Okay. So, high cycle fatigue typically in the case of vehicle loading has been seen, okay, and low cycle fatigue typically in the case of earthquake is seen here. Okay. So, basically these are the progression of the plastic strain or the elastic strain. Okay. So, low cycle fatigue progression of the small localized plastic strain, high cycle fatigue is marked by the small localization of the elastic strain. Okay. Creep failure. So, creep is an time dependent formulation in which the failure occurs, okay, due to the time dependent deformation under the sustained loading. Okay. Okay. So, let us say in this curve, okay, we are monitoring the deflection versus the time. Okay. So, when the specimen is loaded, there will be an initial extension. Okay. So, after that there will be a period, as the time grows there will be a period of primary creep, there will be a period of secondary creep. Basically it is saying that with the sustained load, okay, there will be a deformation in the structure. Okay. So, for the initial time phase, okay, we call this deformation as the primary creep. Intermediate time span we call it as the secondary creep, okay, and after that there is a period of the tertiary creep. Okay. So, creep we are defining in terms of 3 stages. Okay. So, these are the equation for the 3 stages: primary creep, secondary creep and the tertiary creep. Okay. And there is a creep rupture in high temperature structures. Okay. If the structure is subjected to high temperature, there is a phenomena of creep rupture occurring. Okay. So, this is how the creep failure is being defined. So, after that we are discussing about the truss failure mechanism. Okay. So, in the truss failure mechanism there will be a tensile ending in the members, the compression members will buckle, okay, and then there will be a connection or the joint failures. Okay. There is an inbuilt redundancy in the hyperstatic trusses, okay, but nonetheless if the loading is been increased, okay, it will fail in this sequential manner. Okay. Yielding will occur in the tensile members and the buckling will occur in the compressive members, and then it will be propagated to the joints and the connections. Beam failure mechanism, this is the most well known failure mechanism. Okay. So, there will be a flexural failure, okay, which is this type of straight failure, okay, diagonal tension failure, okay, from the loading, this is the diagonal region will occur, shear tension failure, okay, from the point of load application to the supports it will propagate. Okay. So, this is the shear tension failure, okay, and there is a shear compression failure where the crushing of the member occurs, okay, and it is propagating towards the supports. Okay. So, flexural yielding, shear failure, okay, and the section might also fail in the deflection and the serviceability criteria, and there might be the formation of plastic hinge which will lead to the collapse. Okay. Plastic hinge we have already studied. Okay. It means that when we start loading a structure, okay, let us say this is my beam, okay, and I start to load this structure, okay, I start to increase my P, okay, P I am increasing, okay, the magnitude of the P I am increasing. Okay. So, what will happen is that first the top section will undergo compressive loading and bottom section will undergo tensile loading. Okay. As the concrete is bad in tension, okay, so the cracking will start to form out here. Okay. After some time, if the loading is significantly increased, okay, then this plastic region, okay, here it will reach the elastic limit, okay, and the plastic region will start to propagate into my sections, okay, into the sections. Okay. And here what we normally do is that we ignore the contribution of the concrete. Okay. So, all the tension is taken by my reinforced section. Okay. So, once the entire section has reached its plastic limit, okay, we say that a plastic hinge has formed in my section. Okay. And here we say after the plastic section, the section is no longer able to take more loading, okay, and a failure mechanism has been reached. Okay. So, this is the formation of the plastic hinge, okay, that might occur in a reinforced concrete section. Okay. After that we are talking about the slab and the plate failure. Okay. So, punching might occur in the slabs. Okay. So, due to punching shear the failure occur. Okay. So, here a punching case is shown, okay, in which for a localized area, okay, it is not able to take the applied vertical loading, okay, and it fails by the expulsion of a element. Okay. So, this is called the punching failure. There will be a flexural failure in the reinforced slabs. Okay. The deflection limit of the slab might be exceeded, okay, and there are cracking patterns under the different types of loading. Okay. So, punching shear and flexure failure will occur, deflection limit as set by the criteria might be exceeded, okay, and there will be different cracking patterns under the applied loading. In continuation to that, there might be the diagonal tension failure. Okay. So, the shear capacity, okay, that is a contribution from the concrete part and the steel part. Okay. So, it might be exceeded. Okay. So, we need to have the proper shear reinforcement. Okay. So, due to the lack of shear reinforcement, okay, the capacity might be breached and there might be a shear type of failure in the slab and plates. Okay. Progressive collapse. Okay. So, this is also called a domino type of collapse. Okay. So, what happens? Okay, as we discussed earlier, if we have a framing system, okay, if we have a framing system, okay, and it is designed for a certain loading condition, okay, or an envelope of different loading conditions, okay, what we do is that whatever loading condition we have, okay, whatever loading condition we have, we put all the combinations of the loading combinations out here. Okay. After that, we calculate the demand on all of the sections. Okay. We calculate the individual demand on all of the sections, and after that we try to put members so that the demand to capacity ratio is met. Okay. Okay. So, typically what we do is that we keep this demand to capacity ratio such that the demand is lower than the capacity. Okay. So, demand is typically lower than the capacity, and in order to achieve an economical design, okay, normally most of the time what happens is that in the most critical sections, okay, so demand will be very much close to the capacity, okay, and there will be some sections where demand is very less than the capacity. Okay. So, there might be a disproportionate sizing out here. Okay. After that, if one member fails, okay, if one member fails, okay, then there will be a redistribution in the loading. Okay. So, if the redistribution occurs, okay, then in some of the critical sections the demand might breach the capacity. Okay. The demand might become more than the capacity. Okay. Or if this does not happen in stage 1, okay, after the failure of one or two more elements, okay, there will be cases where the demand becomes more than the capacity in only some of the sections. Okay. So, in those sections, in those overstressed sections, there will be a failure. Okay. So, once this is breached, okay, then there will be again a redistribution of the loading. Okay. And due to this redistribution of the loading, again in some more sections the demand will breach the capacity, the demand will become more than the capacity. Okay. So, it will keep on propagating along the entire sections such that the entire structure might fail. Okay. And after failure it might lead to collapse also. Okay. If there is a significant increase in the demand with respect to the capacity, the entire section might collapse also. Okay. So, here we are showing a case of collapse. Okay. So, there might be there are different mechanisms of collapse. Pancake collapse means that this will collapse like a pancake. Okay. From top to bottom it will collapse like this. Okay. Or for a domino type of collapse where it will collapse in some given pattern. Okay. So, some of the historical examples are Ronan point collapse, or the most well known collapse is the WTC collapse, okay, which happened during the 9/11 attack. Okay. So, in the 9/11 attack the whole thing collapsed like a pancake. Okay. So, what happened was that each of the slab system were there, okay, each of the slab system was there, okay, and it was joined by an framing action. Okay. So, due to the excessive heat, okay, what happens was that the connections were no longer able to take the load. Okay. So, they became overstressed, and one slab on top of the other slab, okay, kept on pounding. Okay. So, due to the fire, the initial collapse started, and after that, due to the self weight and the pounding effect, the entire system collapsed like a pancake. Okay. So, this is one of the most well known collapse. Okay. Keep in mind that the failure of the WTC, okay, did not essentially occur due to the impact. The initial impact, it was able to survive, okay, but due to the excessive fire, okay, and the collapse of the connections, okay, the entire collapse mechanism started, the entire progressive collapse mechanism started. Okay. So, this highlights the importance of robustness. Okay. So, the different aspects like fire aspects, the proper designing of the connection has to be ensured in the design. Okay. So, dynamic failure mechanisms, okay, we have already seen the failure mechanisms under the impact loading. The spalling will occur. Okay. So, from here the chunks will go out, okay, scrabbing will occur, chunks will go out, and from the other end again some chunks will go out, perforation, the entire thing will be punching, a section of the things will try to come out, okay, as a punching failure, and this is the overall bending response. Okay. So, this first four can be considered as a local mechanisms, and this is the overall mechanism. Okay. So, due to the impact loading, this type of failure will occur, and due to the blast and the seismic loading, okay, so here a case of the blast loading is shown, okay, where spalling is occurring, okay, in the outer face, and in the inner face there is a compressive damage, compressive cracks has been formed, okay, and on the other face the flexural cracks has formed due to the tensile failure. After that, the shear compression damage failure has been formed, okay, and here we can see plug damage also, okay, and this is a case of the inclined flexural cracks failure. Okay. So, due to different types of mechanism, due to impact mechanism, due to blast mechanism, the different type of failure mechanisms can be shown. Okay. So, in addition to blast and impact, due to the resonance and fatigue also the failure might occur. Okay. So, here the failure in the connections are shown. Okay. So, this is a bearing failure, okay, tensile failure, shear out failure. Okay. Here the entire section has been sheared out. There is a cleavage failure. Okay. So, only one line of failure is there. Here the bearing area has failed. Okay. A tensile split is being observed out here, and this is a combination of the cleavage and the tension failure. Okay. So, combination of these two failure, and sometimes the bolt will also fail. Okay. So, these are the cases of the failure in connections. Okay. So, we are looking into one example of a flexural failure. Okay. So, RC beam is been given with the required dimensions and the reinforcement. We are asked to calculate the ultimate moment capacity of the section. Okay. So, first what we do is that we calculate the neutral axis of the member. Okay. So, this is assuming that the top section has reached the section, the limit state is defined as either the compressive failure will occur in the top portion or breaking will occur in the steel. Okay. So, this is the definition of the limit state function. So, depending upon this limit state function, the stress strain curve is being drawn, and from that particular stress strain curve the moment capacity is being calculated. Okay. So, whenever an ultimate moment is being asked, we have to define the limit state function, or we need to know the limit state function corresponds to which the moment capacity is found. Okay. It means that when this moment capacity is reached, we need to know what are the strain and stresses in my member. Okay. So, for a conventional design, we assume that the crushing in the compressive region or breaking of the bar is being occurring. Okay. So, this is the equation for the neutral axis. We calculate the neutral axis depth. We check the limit such that the section remains unreinforced. Okay. Normally, we design for a balanced section or an unreinforced section. Okay. And using this equation, which corresponds to this particular state of stress, we calculate the moment capacity of the section. Okay. So, here we said that we are assuming that the steel, either the breaking of the steel will occur or crushing of the concrete will occur. Okay. So, here we are getting an ductile flexure design, and this design is desirable from a safety perspective. Okay. Similarly, here in this example we are calculating the elastic buckling failure. So, given the pin condition of the columns, okay, we are calculating the buckling load carrying capacity of the column. Okay. So, let us say the design axial load is 1200 kilonewton, okay, and the buckling capacity is 1.7 meganewton. It means that the column is safe against elastic buckling. Okay. It means that if a load of 1200 kilonewton is applied, okay, this is not going to buckle, okay, since the capacity, the buckling capacity is way more than the applied axial load capacity. Third example, puncturing shear at the interior column. Okay. A flat slab is given with the criteria. Okay. So, what we do is that we take the perimeter, okay, the critical perimeter, okay, depending upon the dimensions we take the critical parameter, and then we have the capacity, okay, the shear capacity, and for an applied load of 600 kilonewton we check for the capacity. Okay. So, the puncturing shear demands, okay, the demand is 600 kilonewton, the capacity of this particular section is 575 kilonewton. So, this is likely to fail in the punching failure mechanism. Okay. So, here we need to add the shear reinforcement in order to prevent this section from undergoing punching failure. Okay. So, fatigue failure. So, here we have to take help of our ascent curve. Okay. So, we have an interpretation of the ascent curve. Okay. So, the stress range is given. Okay. So, the fatigue life can be evaluated using the equation of the ascent curve. Okay. So, the expected life cycle, if this is acceptable, okay, so this is the fatigue life of the total fatigue life of the structure. Okay. So, if requirement is of this magnitude, okay, then it will survive this life. Okay. Okay. So, in this particular example, the critical stress for a thorough crack has been evaluated. Okay. So, we have been given an edge plate crack, the modification factor K1 is 1.12, fracture toughness KIC is given by this equation. Okay. So, critical stress for the fast fracture is 356 MPa. Okay. So, if the service stretch may approach 350 MPa, then there is a risk of brittle failure occurring in this particular region. Okay. So, this way we can assess the hazard in the limit of the hazard, we can assess the limit of the hazard depending upon the sectional capacity, and we can design such that this type of failure mechanisms are not met. Okay. So, today we looked into the different failure mechanisms. Okay. We dealt with the different failure mechanisms when they are occurring, and we also looked into some of the examples dealing with the different types of failure mechanisms. We tried to evaluate the critical loads during these failure mechanisms, and also suggested how these failure mechanisms can be averted. Okay. So, I request you to go through these examples. Thank you.